Hello, you're listening to the Science of Everything podcast, episode 144, Anthropogenic Climate Change. I'm your host, James Fodor. So, this will be the final episode in our series looking at climate change, and today, as indicated, we're going to be talking about anthropogenic or human-caused climate change, with the focus particularly being on how we know specifically that the warming of the climate over the past century or so is due predominantly to human causes. And we'll also then talk about, given that we know the primary causes of the changes in the climate, what can we project about how those changes will continue over the coming century? So future projections and effects on extreme weather, the oceans, ecosystems, and so forth. So the projections and impacts of continued warming brought about by continued greenhouse gas emissions. So that's the second part of the episode. And we'll also talk a little bit at the end about mitigation and the costs and benefits thereof, though the focus won't be on like the pros and cons of different technological solutions, but rather just on an overall estimates of how effectively we can mitigate impacts of climate change and what the relative cost and benefits of that would be. So the recommended pre-listening is the previous episode 143 on climate modeling. It's all part of a series, so that will be helpful to understand the context. Now, with that introduction out of the way, let's get into it and start talking about what is sometimes called the fingerprints of human-produced warming. So throughout the series, we've talked about the history of the Earth's climate, the mechanisms of climate change, the greenhouse effect, and then how we model and measure climate change and the alterations on Earth's climate. And we've said a lot about the fact that greenhouse gas emissions have been increasing. We have a very clear model from the greenhouse effect about how greenhouse gas concentrations in the atmosphere affect temperatures. We have used climate models of a range of different types and sophistications to establish that the increase in greenhouse gas emissions very well explains the increase in temperatures over the last 100 years or so, whereas other potential causes, such as solar forcing, orbital changes, and so forth, don't explain the increases in temperature that we've observed. The final piece of the puzzle, if you like, is to go through some additional specific evidence that warming is actually human caused. So it's one thing to say that we have a good model and a theoretical understanding of how increased greenhouse gas concentrations in the atmosphere produced by burning of fossil fuels could lead to warming, and that the modeling suggests that the amount of warming we see because of that matches the amount of warming we'd expect to see given the understanding we have of the atmosphere. Nevertheless, one can still question whether there's any more direct evidence that, in fact, the warming is being caused by humans specifically and not perhaps some unknown cause. And indeed, there are a number of lines of evidence that strongly suggest that overwhelmingly the warming that we have been observing and continue to observe is caused by human production and release of greenhouse gas emissions. So let's go through and talk about some of these so-called fingerprints of human-produced warming. So the first is that we've observed that the amount that the planet is warming is greater during the nights than during the days. Specifically, when we measure warm nights, the number of warm nights relative to seasonal norms has increased more than the number of warm days, and likewise the number of cold nights has decreased more than the number of cold days. So there's a greater warming at night in many parts of the world than during the day. And this is expected if it is indeed greenhouse gas emissions which are responsible for increased warming. The reason for that is because the radiative effect of long-wave radiation being emitted by the surface of the Earth and warming up the atmosphere surrounding the surface of the Earth, that occurs both at night and during the day, so you expect warming both times. And it turns out, for somewhat complicated reasons, that the amount of warming you expect during the night proportionally is actually larger than the amount of warming you expect during the day. The reason for this has to do with the fact that the volume of air that's in kind of radiative contact with the ground, the so-called boundary layer, is much smaller during the night, and that means that it's proportionally warmed more by the Earth's surface compared to the much larger volume of air that is in contact with the surface of the Earth during the day. So sort of less air is warmed more during the night than the much larger amount of air is warmed during the day, proportionally speaking. Now, if global warming were caused by increases in solar irradiance, you would not expect to see that. Obviously, because solar irradiance only operates during the day. Therefore, if that were the case, we'd expect to see days warming up much more than nights, but that's in fact not what we see. And so that's consistent with warming being caused by an increase in the greenhouse gas concentrations in the atmosphere. Another line of evidence is the fact that the stratosphere is cooling. So the stratosphere is the layer of the atmosphere immediately above the troposphere. Troposphere being where we are, where most of the weather happens. The troposphere is the lowest part of the atmosphere, and it's the region that's been warming in recent decades and centuries. The stratosphere, by contrast, has actually been cooling. Now, that may seem a little bit counterintuitive. Well, if the Earth is sort of building up radiative energy from the sun because of greenhouse gases preventing it from being emitted, then why would the stratosphere be cooling? Well, it's a bit of a complicated effect as to why this happens. Let me try to explain it. So to understand why we get this difference in the effects of increased greenhouse gas concentrations of the troposphere versus the stratosphere, we have to understand what is the difference between what is happening at those two layers. Now, in the troposphere, most of the energy that's absorbed comes from the long-wave radiation that's emitted from the surface of the Earth. So that means if you increase greenhouse gas concentrations in the troposphere, you get more absorption, which leads to heating, right? That's the greenhouse gas effect that we've just been talking about in previous episodes, okay? But in the stratosphere, there's a significant difference. Specifically, the stratosphere contains large concentrations of ozone. That's the gas O3. And ozone is a good absorber of shortwave radiation from the sun. So as we talked about in previous episodes, the troposphere is largely transparent to shortwave radiation from the sun, so it sort of goes right through. But that's not true for the stratosphere. The stratosphere actually, because of the ozone layer in the stratosphere, you've probably heard of that, it absorbs significant quantities of shortwave radiation from the sun, which warms up the stratosphere. So the stratosphere actually, it gets hotter with the temperature rises with increasing altitude as opposed to the troposphere, which does the reverse. So the stratosphere at higher altitude is actually quite hot. And that's because of the absorption of the shortwave radiation from the sun by ozone molecules in the stratosphere. Those ozone molecules aren't in the troposphere, or at least in much lower quantities. This higher temperature of the stratosphere also means that the stratosphere is a much more effective emitter of long-wave radiation compared to the troposphere. Because remember from the Stefan-Boltzmann law, which we've talked about in previous episodes, if you increase the temperature of a body, the amount of radiation that it emits increases by the fourth power of the temperature. So in other words, in much, much greater proportion to the increase in temperature, the amount of radiation emitted increases much, much more. So this means that the stratosphere heats up because of the ozone absorbing shortwave radiation from the sun, which doesn't happen in the troposphere, which makes the stratosphere a much more effective emitter of long-wave radiation compared to the troposphere. Okay, so why is that? Why does that make it so that the stratosphere actually cools down with increased greenhouse gas concentrations? Well, think about what happens when the greenhouse gas concentrations increase in the stratosphere versus when they increase in the troposphere. When greenhouse gas concentrations increase in the stratosphere, that doesn't much change the amount of radiation that's absorbed there. A lot of the radiation's already, but by contrast, the high temperature of the stratosphere means that the amount of radiation that's emitted increases much more. So essentially, because of its increased temperature, which results from the ozone layer there, the stratosphere is a much better emitter of long-wave radiation than it is an absorber. So when you add more greenhouse gases to the stratosphere, it actually decreases in temperature because the effect of being because the amount of emission that's happening is kind of greater than, or it's outweighing the effect of the amount of absorption that's happening. Whereas in the troposphere, it's the opposite. Greenhouse gases are a better absorber of long-wave radiation than emitters in the troposphere, where temperatures are lower, and therefore an increased concentration of greenhouse gases in the troposphere leads to an imbalance of the absorption compared to the emission of long-wave radiation, thereby leading to an increase in temperatures. So it's really all about what's happening in that layer of atmosphere. Because of the ozone layer in the stratosphere, that means that it absorbs lots more shortwave radiation from the sun, which heats it up, which makes it a much better emitter, which means when you add greenhouse gas to the stratosphere, the emission effect, the increased ability to emit radiation resulting from those higher temperatures, outweighs the increased absorption from the increased concentration of greenhouse gases. And so you get a net reduction in temperature to balance those out. Whereas in the troposphere, it's the opposite. When you add more greenhouse gases, the increase in absorption outweighs the increase in emission, and so you need an increase in temperature to balance that out. So that's why we see this difference between the stratosphere and the troposphere. It all relates to what other gases are present, what wavelengths are they good at absorbing versus emitting, and then how is that effect altered by increased greenhouse gas emissions? In each case, it's altered by the increased concentration of greenhouse gases, but in different ways. In the stratosphere, more greenhouse gases tips it in the emission direction, and therefore to maintain equilibrium, temperatures go down. Whereas in the troposphere, adding greenhouse gases tips it into the absorption direction, which means that temperatures have to increase in order to balance it out again. So that means that we have this difference of more greenhouse gases leading to a warmer troposphere, but a cooler stratosphere. And that is in fact exactly what's been observed in recent decades, is that the stratosphere is indeed cooling, whereas, as we've discussed at length, the troposphere is warming. We also discussed this in the issue of modeling, well, the greenhouse effect, and also modeling the climate and validating climate models, because satellite measures of changes in temperature have to be carefully adjusted so that they don't accidentally measure some of the reductions in temperature occurring in the lower stratosphere and attribute that to the troposphere, because that would be measuring the wrong thing, essentially. We want to check what's happening from the troposphere separately to the stratosphere, because there's actually different predictions there about the effects of greenhouse gases. And this is not what you would expect to happen, once again, if the warming was caused by increased solar irradiance. You wouldn't see this cooling of the stratosphere in the same way. Because the stratosphere is good at absorbing shortwave solar radiation, you'd expect the stratosphere to increase in temperature. Okay, so moving on to the next fingerprint of human-produced warming, increase in the height of the tropopause. So the tropopause is just the boundary between the troposphere and the stratosphere. It's not correct to think of it as, like a border between countries or something like that. The tropopause moves and changes depending on temperature and time of day and season and things like that. And it's at different altitudes, at different latitudes on the planet and things like that. So it's sort of a movable boundary. But at any rate, it's still an important feature of the climate system. It's marked by a temperature inversion, whereas remember that the temperatures decrease as you increase in altitude in the troposphere until you get to the tropopause, where they start increasing again. And that's what marks the tropopause. It's this shift between temperatures decreasing to temperatures increasing. Now, it turns out that if you combine warming in the troposphere with cooling in the stratosphere as a result of higher greenhouse gas emissions, the combined effect of those is an increase in the height of the tropopause. That is, it occurs at a higher, this temperature inversion occurs at a higher altitude than previously. And to understand that, you can just imagine the letter X, right? If you move from left to right, there's a sort of the upward sloping half of the X and the downward sloping half of the X, viewed from left to right. So the downward sloping half of the X represents the lapse rate. So that represents the fact that the temperatures decrease with increasing altitude in the troposphere. And then the upward sloping half of the X represents the lapse rate in the stratosphere. Temperatures go up, right? So temperatures go down in the troposphere with altitude, but they go up in the stratosphere with altitude. Technically, those will only look like the right half of the X, right? Where it first goes, where you could imagine tracing it like the right half of the letter K, right? It goes sort of diagonally upwards and backwards and then diagonally upwards and forwards. So hopefully you can visualize what I'm saying there. That's sort of what the lapse rate looks like. But anyway, let's imagine that letter X again. Now, let's take the two halves of the letter X, the two diagonal lines, and pull them apart from each other. Slide them one to the left and one to the right. You're sliding them apart. What happens to the intersection point, that kind of middle of the cross? Well, as you slide the two sides, the diagonal halves of the X away from each other, that intersection point, which represents the tropopause, that's where these two lapse rates intersect with each other, the tropopause will go up, right? If you're sliding these diagonal lines away from each other, that's just sort of what happens. And this represents the fact that the troposphere is getting warmer and the stratosphere is getting cooler, and so the intersection point will be at a higher altitude. It's not really that complicated. It's a little bit hard to explain. Hopefully you get the idea. But the point is, this is just another consequence of the fact that the troposphere gets warmer with increased concentrations of greenhouse gases, whereas the stratosphere gets cooler. The consequence of those will be a higher altitude of tropopause. And we've in fact measured that the tropopause height on average has increased by several hundred meters in the past 3 decades. Exactly what would be predicted if warming is being caused by increased greenhouse gas concentrations. Another thing that we can look at to determine whether or not temperatures are rising due to increased greenhouse gas concentrations is to directly measure the energy budget at the top of the atmosphere. We can measure the flux of long-wave radiation that's being emitted to space and compare it to the amount of radiation that's being absorbed. What we would expect to see is an imbalance resulting from the additional absorption of long-wave radiation going out into space, or not going out into space, being prevented from going out into space because of the higher concentrations of greenhouse gas emissions. And we can measure that using satellites, and in fact, that is precisely what we've measured. The energy imbalance is currently estimated at about 1 watt per meter squared at the top of the atmosphere. And this imbalance has been increasing for several decades with higher greenhouse gas concentrations and is predicted to increase for some decades to come, depending on exactly how emission trajectories look over the coming decades. One final piece of evidence, this isn't so much evidence for warming as such, but it's evidence that the changes in carbon dioxide in the atmosphere are produced as a result of human emission of carbon dioxide as a result of burning of fossil fuels. I don't know that there should be too much doubt about this because, we know how much the greenhouse gas concentrations are going up in the atmosphere, and we can measure the absorption of carbon dioxide in the oceans as well, and we can compare that to emissions, and we have a pretty good idea of where everything's going and what the balances are. But as an extra piece of evidence, you can also look at the isotope ratios of carbon, particularly looking at carbon-14 compared to carbon-12. Carbon-14 is an unstable isotope of carbon which is produced in the atmosphere as a result of cosmic rays. It decays fairly quickly on geological time spans. It has a half-life of about 6,000 years. This is the isotope that's used for carbon dating. So once carbon has been fixed in some form, be it in a physical artifact or in fossils that are then buried in the earth, it ceases to pick up new carbon from the atmosphere, and thereby its carbon-14 quantity will progressively decrease. When an organism is alive, you constantly interchange carbon atoms with the atmosphere, and so you bring in new carbon-14 just as you're breathing out old carbon-14, and some of it's decaying, right? But you maintain an equilibrium with the atmosphere. But once carbon is fixed in some form that's non-living, such as a fossil, that ceases, and so the amount of carbon-14 thenceforth only decreases over time as a result of radioactive decay. So there should be no carbon-14 in any fossil sources of carbon because they were buried millions and millions of years ago, so it's all decayed away by this point. This reduction in the relative quantity of carbon-14 in the atmosphere as a result of burning carbon-14 depleted fossil fuels is known as the Suess effect. I hope I'm pronouncing that correctly. That's SUESS. And this has been measured in the past few decades, and there's a noticeable reduction in the proportion of carbon-14 in the atmosphere on the order of, I think it's a few percent or something like that. This actually has a potential to disrupt carbon dating in the current decades because of the reduction in the amount of carbon-14 that organic life will naturally have as a result of less being in the atmosphere. But that's actually interesting. So that's further evidence that the increase in the carbon dioxide that we're seeing in the atmosphere is directly a result of fossil carbons being burned and released into the atmosphere by humans. And then, as we've seen, the other fingerprints of warming, particularly the greater rate of warming at night, the cooling of the stratosphere, and the increase in the height of the troposphere, all point to the increased temperatures being the result of increased concentrations of greenhouse gases. That all comes in addition to the fact that when you look at the changes in solar irradiance or rates of volcanic eruptions or other effects that we know of that have impacts on the climate, they're all far too slow and or far too small over the past century to account for any significant quantity of the changes in temperature. And the modeling that we have done using a range of different assumptions and ways of approaching the climate, from very simple to much more complicated, all support these estimates of how much of the changes in temperatures can be explained by natural versus anthropogenic forces. And overwhelmingly, they indicate that the changes in temperature over the past century or so are the result of increased concentrations of greenhouse gases in the atmosphere caused by human activity. So that brings us to a close of the first half of this episode, which is talking about the evidence for climate change being primarily the result of human causes, particularly burning and release of greenhouse gases into the atmosphere. Now, the next side of this coin is looking into the future and asking the question, well, given that we know what the primary cause of recent climate change is, what can we expect to happen in the coming decades and even centuries, given that we will continue to emit greenhouse gases, at least for the foreseeable future? This begins to now involve certain political questions involving how much rates of emissions will decrease and things like that. But nevertheless, it's important to get a sense of what the trends have been, what they are likely to be, and then what the impacts will be on the planet, ecosystems and humans and so forth as a result of continued warming and continued increases in carbon dioxide concentrations. Let's have a look now at what the evidence shows about recent trends and future projections regarding human emissions of carbon dioxide and other greenhouse gases. When we look at different regions in the world over the past 20 years or so, we actually find an interesting range of trends. So many people may not know this, but the rate of increase in greenhouse gas emissions has substantially slowed over the past couple of decades, especially when you look at a per capita rate, so per capita meaning per person. So China's greenhouse gas emissions per person were increasing very rapidly over the 2000s, but over the past 10 years or so, the rates of growth is fairly small, only about 1 to 2% per year, which is still in the wrong direction, but the Chinese government appears to be pretty intent on bringing down its greenhouse gas emissions over the next few decades. If we look at developed countries, so the US and the European Union, both have seen reductions in per capita CO2 emissions over the past 20 years of in the range of 3 to 4%. Other countries such as India and Russia and much of the rest of the world have seen a relatively constant level of per capita CO2 emissions. So there aren't actually many countries these days, or at least not many large countries, where per capita CO2 emissions are still rising at a rapid rate. In most countries, they're either roughly static or going up a little bit, like China and India, and in many developed countries are actually coming down. Now, if you look at total fossil fuel emissions, which is a different question, because this is multiplying by population, we see a similar trend, but with some modification. So now, in many poorer countries where there's more rapid population growth, such as India, you see more rapid rates of CO2 emissions, because although per capita increases aren't very rapid, population increases sort of make up for that. India's emission of CO2 has increased a fair bit over the past 20 years or so, whereas the European Union and the US have again decreased their absolute levels of CO2 emissions in addition to per capita reductions. China's overall CO2 emissions have increased tremendously over the past 20 years or so. I think they've something like tripled in the past 20 years. However, now that China's population is actually declining, as well as the fact that their per capita CO2 emissions are peaking or only increasing slightly, China's total CO2 emissions are not increasing very rapidly at all. And in fact, they may start to decline this decade. Countries like Russia, some middle-income countries like Russia are seeing fairly static populations and not particularly large changes in per capita emissions, so their total emissions are roughly stable. The rest of the world is seeing somewhat of an increase in total CO2 emissions, but that's largely driven by population growth, especially in sub-Saharan Africa and certain parts of Asia, more so than by increased per capita CO2 emissions. So the overall picture is mixed. It's certainly, we are still seeing overall increases in CO2 emissions and fossil fuel emissions more generally year on year, which is not what we want to see. But on the other hand, the rate of increase has dramatically slowed compared to what it was 20 or 30 years ago. And furthermore, pretty much all developed countries have seen substantial reductions in both the per capita and the total CO2 emissions in the past 20 years. There are individual exceptions, and we don't have time to go through every single country, but this is the overall trend. So the trend is good, but the downside or the problem is that the reductions have not come fast enough. So in 2015, all countries in the UN negotiated the Paris Agreement, which is a replacement of the Kyoto Protocol you may have heard of from back in the 90s. The Paris Agreement aims to keep global warming well below 2 degrees Celsius, which is sort of the danger threshold that's been identified by the IPCC. And the aspirational goal is to keep warming under 1.5 degrees Celsius relative to pre-industrial levels. Remember that we're already at 1.2 degrees of warming relative to pre-industrial levels, so we're already quite close to that aspirational goal. Now, in order to meet this 2 degrees goal, emissions will have to peak, so total fossil fuel emissions have to peak by about 2025. So in other words, they need to peak pretty much now or next couple of years at most. And this looks very unlikely to happen. However, if you look at current trends as well as pledges and changes that are happening at governmental and industry levels, it does look like emissions will be peaking roughly in the 2040s, which will lead to about 3 degrees of warming by the end of the century. So that's 1 degree higher than the 2 degree target and significantly warmer than the 1.2 degrees that we already see. However, that is a substantial improvement over what the situation was looking like back in the 1990s and early 2000s. At that point, it looked like that emissions would keep growing exponentially, leading to more like 5 degrees of warming by the end of the century. So, at the moment, we're in a kind of a glass half full, glass half empty situation. On the glass half full side, we've cut the amount of expected warming by the end of the century from something like 5 degrees to more like 3 degrees. And that's a very substantial change. When we come to look at the costs and impacts of warming, the costs and impacts of warming of 5 degrees are dramatically higher than those of 3 degrees. So that's already, the reductions that we've seen will already be enough to make a significant difference. So that's good news. On the other hand, the glass half empty side, the rates of emissions reduction have come much slower than they need to in order to meet this treaty that was signed back in 2015, agreement to keep warming below 2 degrees. And it looks extremely unlikely that that's going to happen. There are still ways we could potentially achieve that, but that's probably going to involve active removal of carbon dioxide from the atmosphere, or more drastic measures like geoengineering, but we're not really going to get into those in this episode. But at least through more traditional means, it looks very unlikely that we'll be able to achieve that objective, because it would mean emissions peaking essentially now and then gradually declining over the next few decades. It's important to understand that there's a few different sort of phases that we need to go through as a planet, really, as a people, as humanity, in order to decarbonize the economy and achieve a sustainable climate. The first thing that needs to happen is that, well, I guess the very first thing is that the rate of growth of emissions needs to start slowing down. Previously, up till, let's say, around the year 2000, for most countries in the world, emissions were increasing exponentially with economic growth and population growth. And that was obviously unsustainable. I mean, you can't keep doing that forever, or even for very long. The first thing that needs to happen is to get off that growth trajectory and start slowing the rate of growth of emissions. And that, thankfully, has already happened in the vast majority of countries, both developed and developing countries. The rate of emissions growth has dramatically slowed. The next thing that has to happen is you have to go from slowing down the rate of growth of emissions to actually stopping the rate of growth of emissions. And so this is when we reach peak emissions. That's when the rate of emissions is the highest that hopefully it will ever be. Once peak emissions has occurred, we've now stopped the rate of growth of emissions. That's good, but it still means that we're emitting a very large amount of carbon dioxide and other fossil fuels and other greenhouse gases into the atmosphere each year. So that means that we're still going to get a very large warming effect from that. In order to actually reduce the amount of total warming in the future, we need to reduce emissions, not just stop them growing as fast, but actually reduce them substantially. Really, the objective needs to be to bring those emissions down to net zero. So you will hear people talking a lot about going to net zero with various dates between 2030 and 2050. I usually hear people talking about 2030 is, I think, not realistic for the vast majority of countries. But at any rate, that net zero refers to a net zero emission of greenhouse gases into the atmosphere. Net zero is important because it doesn't mean that we literally emit no carbon dioxide. That wouldn't be feasible. There are still certain industrial processes that will need to continue that result in emissions of greenhouse gases. It just means that for whatever amount of carbon dioxide or other greenhouse gases we emit into the atmosphere in a given year, we withdraw the same amount of carbon dioxide from the atmosphere. And that can occur through afforestation, or it could occur through carbon capture, land use changes, and other means like that. So that's the goal, to get to net zero. Once we've then got to net zero and we give the climate some time to adjust, even then, we still will have a certain amount of warming that's kind of built in as a result of the greenhouse gases that we've already emitted. And if we sort of did nothing at that level, it would take centuries, I think millennia, for that excess carbon dioxide to be removed from the atmosphere. And it would take a very long time, actually, for all of the effects to be felt and equilibrium to be reached, because there's an effect of when you put carbon dioxide in the atmosphere, it takes a while for the planet to warm up to reach equilibrium with that increased amount of carbon dioxide. But then there's also the effect that carbon dioxide will be removed from the atmosphere through natural processes if you don't keep replenishing it. And that's all a very complicated story that takes sort of centuries to play out. And I guess, at that point we'll have to decide as a planet, well, what sort of atmosphere do we want to have, and Can we sort of optimize it for human benefit? But that's, long term in the future. The priority at the moment is to first stop the rate of growth of emissions, so to reach peak emissions, and then to reach net zero. Those are the priorities. And pretty much all of the scenarios that are plausible at the moment see all of those things happening. So net zero, so emissions peaking and then net zero being achieved. All the plausible scenarios show those happening this century. And it's not even just climate consciousness that's leading to that. There's many economic incentives that are leading to increasing uptake of renewable energies as well as depletion of fossil fuels and all sorts of other factors, right? Geopolitical as well. So the point is there are many reasons why many parts of the world are progressively moving away from fossil fuels, though fairly slowly, but steadily. And that's almost certainly going to happen by the end of the century. The real question is, when is it going to happen? The sooner it happens, the lower the level of atmospheric concentrations of greenhouse gases that we equilibrate at, therefore the lower the equilibrium temperature we will have. And as projections show at the moment, given trends and current pledges of different countries, what we're looking at is, by the end of the century, temperature rises of about 3 degrees relative to pre-industrial levels. So that's another 1.8 degrees or so relative to what we have, to the amount of rise we already have now. And that corresponds to an atmospheric concentration of carbon dioxide of, I think, something like 600 or so. That's significantly higher than the concentration that we have at the moment of about 420. So we can expect that to go up to at least 500 to maybe 600 by the end of the century, resulting in about 3 degrees of warming. So that's what we can expect given current trends and projections and commitments. Now, whether those will be fulfilled or whether we'll go above and beyond those, obviously we don't know that yet, but that's sort of roughly the trajectory we are on. So things are looking a lot better than they were 20 years ago, but at the same time, we're progressively losing the opportunity to bring that net zero year earlier and earlier. To reach that 2 degrees goal, we basically need to be reaching peak emissions essentially now. I think 2030 at the absolute latest to be below 2 degrees. But it looks very unlikely that that's possible. Emissions peak in the 2040s with reaching net zero, perhaps around 2060, is more what we're currently looking at. And that could probably be moved earlier, but I think it's very unlikely that it could be moved to 2030. So we'll have to see what happens. But the point is that things are looking better than they were, but we also have fewer opportunities than we did 20 or 30 years ago. Okay, so that's kind of the outlook and projections as to what's likely to happen. Let's talk about some of the actual implications of this for the ecosystem, for life on the planet, and for humans. So the most obvious implication of global warming is that, the world will be warmer, sort of unsurprisingly, and that has a number of important effects. So higher temperatures don't just mean that every day it's slightly hotter. And I think that this is a very common misconception, that people hear 1, 2, 3 degrees of warming and they just think, oh, well, an extra couple of degrees, Celsius, so it's more than that Fahrenheit, but an extra couple of degrees every day, that's not such a big deal, right? At most, it might be a little bit annoying, but what real difference does that make? The problem here is that when we're talking about average global temperatures, a 1 or 2 degree increase is a very substantial change. And that's not because you get 1 or 2 degrees or 3 degrees of higher temperatures kind of every day. That's an average. What you actually will get is, many days will be about the same as they always were, and some will be slightly hotter, and those ones won't be that big a deal for the most part. But what's really the issue is that the amount of extreme weather, so very, very hot days, and in some regions also very, very cool days can also be increased. But typically what you see is, on average, many much, much hotter days or periods of time, which has very significant effects. So that, in particular, for things like bushfires or forest fires, as you call them elsewhere. Also, hurricane severity and frequency is thought to increase as there's more energy in the atmosphere. This increase in energy in the atmosphere also leads to changes in rainfall patterns and changing amounts of rainfall between different seasons. So wet seasons are predicted to get wetter and dry seasons get drier. So that exacerbates differences in climate by region as well as by season, and also has effects on crops and expected damage due to storms, hurricanes, flooding, and other things like that. Increasing frequency and duration and severity of droughts is also a very significant issue, especially in relatively drier areas, of which there are many around the world. Heat waves also will increase in intensity and severity, and heat waves pretty much inevitably lead to significant numbers of deaths even in industrialized countries where there's widespread air conditioning, at least in many countries. Countries that don't have that are likely to have even more severe human costs as a result of increasing heat waves and fires and such. So to give an example, if we talk about 50-year heat waves, so that is, I don't know exactly how, this is from the IPCC, I don't know exactly how they define a heat wave, what period of time that is, but regardless of how that's defined, if you look at a severity of a heat wave that comes around every 50 years or so, with 1 degree of warming, which is effectively what we already have, or a little bit more than that, 50-year heat waves are expected to be about 5 times more frequent compared to at the pre-industrial level of temperatures. If we go from 1 degree of warming up to 3 degrees of warming, then those 50-year heat waves aren't 5 times as common anymore compared to pre-industrial times. They're more like 25 times as common. So that's 5 times more common again than they already are compared to pre-industrial times. So that's a lot more of these very intense heat waves. And that's a 50-year heat wave, which is very significant. Well, it was a 50-year heat wave back in pre-industrial times. It's now obviously much more common than that, precisely because the Earth has warmed. Likewise, unusually severe rains, droughts also become much more common with high temperatures. So you shouldn't think of increasing global temperatures as just meaning that there's a slight overall increase in temperatures across the board. I mean, that is what happens, but the effects of that are much broader, and predominantly what it means for most places is more intense, more unpredictable, more extreme weather. And again, not only just hot weather, but also it can include cold weather. So for example, in northern latitudes, warming is thought to lead to an increase in the amount of snow and rain, at least during the winter. So there's many complex effects that it can have, and usually these are bad for humans because they're things that are, at least used to be, relatively infrequent and very severe. So, hurricanes, droughts, fires, heat waves, things like that. So none of these are good news for humans and for human civilization. But honestly, if you look at the different effects of climate change, it seems that it's not even that extreme weather, or the effects on agriculture, which we'll talk about in a moment, that is the worst. It actually looks, at least from my reading of the issue, that the oceans will be the most severely affected. And we don't think about that as often, particularly because we typically measure temperature changes in the atmosphere. That's what all of these temperatures that I've been talking about refer to, changes of temperature in the troposphere. But the oceans are increasing in temperature as well. The oceans absorb a tremendous amount of heat, with the oceans increasing in temperature about half as much as the land surface has and the lower atmosphere has over the past 50 years. So the ocean temperatures are going up as well as atmospheric temperatures, but not quite as much. There are many complex reasons for that, which we don't need to get into here. I've talked about some of them when we looked at climate modeling, for example, and modeling heat transfer in the oceans. It's very complicated, and the ocean is obviously very large. The issues are complicated here because there's sort of 2 different things going on at once. The ocean, it's a sink of energy and it's a sink of carbon dioxide. So there's sort of a double whammy here. The ocean is absorbing carbon dioxide, but some of the carbon dioxide remains in the atmosphere, and that contributes to warming. And some of that energy is also absorbed by the ocean. So the ocean is kind of helping us out doubly. It's absorbing some of the CO2, which would otherwise be in the atmosphere, and contributing to warming. But the ocean is also absorbing some of the extra energy generated by the CO2 that does end up in the atmosphere. So there's 2 of those effects going on. And both of those things have negative consequences for the ocean itself. So let's first take the issue of the ocean absorbing CO2. This causes ocean acidification, because when carbon dioxide is dissolved in water, it produces carbonic acid, which is an acid, which thereby lowers the pH of the ocean. That's acidification. And this is bad news for many marine organisms. Many marine organisms, not all, but many of them are very sensitive to the pH of the ocean. And a decrease in the pH, acidification, can lead to reduced rates of calcification, so that's forming hard body exteriors that help protect many marine organisms. It can depress metabolic rates, lower immune responses, and reduce the amount of energy that's available for functions like reproduction. So many sea creatures are very sensitive to ocean pH, and as the pH decreases, that can have very negative effects on their metabolic function. Now, you might be thinking, but just as atmospheric temperatures and carbon dioxide concentrations have changed historically by very large amounts, we've talked about that in previous episodes, so too, the pH of the ocean has changed, as well as the temperature of the ocean has changed dramatically historically. And, ocean life has always, managed to get by, right? Sure, there have been extinctions and so forth, but is this really a big deal? Things have changed before. Now, if you remembered in the first episode in particular, where we looked at the history of climate, we talked about this issue. Well, the climate's changed before, and in fact, it's changed much more than it's been changing recently. So what's the big deal? The big deal, of course, is the rate of change. It's not the absolute amount so much as the very rapid pace at which temperatures and pH, in this case in the ocean, have been changing. Organisms can adapt if they have enough time. There are certain behavioral adaptations that can occur. They can move to different ecosystems or different regions. Even that takes time. But also evolutionary adaptation, as there's a selection in favor of traits that help the organism survive in the new environment. That's much slower. That takes tens of thousands of years. I mean, evolution happens quicker than that, but for responding to substantial changes, it typically takes thousands to tens of thousands of years. It can sometimes be more rapid, but in general, it takes a long time. Changes in the pH on the scale of decades is far too rapid for evolution to really have much of an effect on that. And so the issue here is that the rate of change is much, much higher than has pretty much ever, or at least in the vast majority of circumstances, than has ever occurred in the history of Earth. And generally, when there have been some instances with very rapid changes in the ocean or in the atmosphere for that matter, it's associated with very dramatic cataclysmic events, such as massive volcanic eruptions or asteroid collisions or other things like that, which have been associated with mass extinctions. So the point is, these changes in ocean pH are a very big problem for ocean life, and this is not precedented, at least not for a very, very long time in geological time, because these changes of this rapidity don't happen very often, only with those sort of cataclysmic events that I mentioned. And so clearly they are bad news. Let's talk a bit about corals. So corals are sessile marine invertebrates, which live symbiotically with photosynthetic algae. The algae provide them with food in exchange for protection, so there's a symbiotic relationship there. However, when temperatures increase, and they don't have to increase by very much for this to occur, the algae begin to produce a certain chemical compounds called reactive oxygen species, which are toxic to the coral. And so the coral expels them. It kicks out the algae because they're basically poisoning them. Now, the algae, the photosynthetic organisms, produce the majority of coloration of the corals. And therefore, when the coral expel the algae because of, they're being poisoned and all that, this leads to what's called coral bleaching. The coral loses most of their coloration. Hence, increased ocean temperatures lead to coral bleaching. Now, sometimes bleached corals can survive or can recover, the algae can return, but in most cases, the algae provide the vast majority of the coral's energy, so bleached corals typically die. So once corals become bleached, it's not necessarily a death sentence, but usually it is. Usually it means that coral is dying or will die soon. So coral bleaching is a major concern in many areas in the world because of increased temperatures in the oceans, resulting ultimately from increased concentration of greenhouse gases in the atmosphere. Some of that energy ends up in the oceans. So that's a major effect there, and corals are very important for ocean ecosystems. So we've talked about two things already. There's ocean acidification and there's coral bleaching, which results from changing temperature of the oceans. Let's talk about sea level rise. Now, that's something that often gets discussed. Sea levels can change dramatically over geological time. During the last glacial maximum, about 20,000 years ago, sea levels were actually about 100 meters lower than they are today. Now, we're certainly not talking about changes of anything on that scale, at least not in the next century or two. However, in the last 120 years or so, average global sea levels have risen by something like 20 centimeters. You might see slightly different estimates because it's actually quite difficult to measure average global sea levels, but the rough rate of increase is about 1 millimeter per year, 1 to 2 millimeters per year. That doesn't sound like a lot, but over many years, that does have an impact. And even relatively small changes in sea level can have very significant implications for vulnerable populations living near the coast. Now, just so we understand the context here, there are many contributing factors behind sea level rise. People naturally think about melting of ice, but actually, at least in the past few decades, thermal expansion of water, this refers to the fact that water literally takes up more space when it is at a higher temperature. This accounts for nearly half of the sea level rise. It is just thermal expansion of water. So that's nothing to do with ice melting. Melting of temperate glaciers accounts for about 21% of sea level rise, and the remaining 20 or so percent being due to melting in Greenland and Antarctica. An important misconception here is that melting of sea ice does not actually contribute to sea level rise because the ice is already fully on the water, right? So whether it melts or not doesn't affect the sea levels. So sea ice itself, so like melting of the sea ice around the North Pole, that doesn't affect sea levels, but melting of glaciers on Greenland or in the Antarctic, or as well as temperate glaciers, that does affect sea levels because that ice is currently on continental plates, and when it moves into the ocean, that raises sea levels. So over the course of this century, sea level rise is expected to be between 50 and 100 centimeters by the end of the century. So, 0.1 of a meter, 10% of a meter, that's not a trivial amount. It's fairly small compared to, the last glacial maximum. But again, that was 20,000 years ago, and we're talking about over the course of a few decades. So even this relatively small increase in sea level rise is enough to potentially displace the entire populations of small atoll nations like Kiribati, Maldives, Marshall Islands, and Tuvalu. They're at risk of being displaced. Their entire island, some of the islands I think will actually be entirely swamped by even a relatively modest increase in sea level, because some of these islands are basically just at sea level. But you have to remember that it's not just the aggregate sea level that's important. Infrastructure has to be sufficiently robust, such as that when you have storm surges or waves and so forth, and changes in tide, that you don't have a vast area of the island becoming inundated. And that can't occur too regularly, otherwise you'll have to move, right? So some people think about this very in an overly rigid way, as if you just you add up the height above sea level of all of the regions of the Earth, and only the regions that are now under sea level as a result of sea level rise are those threatened. That's not true at all. What really matters is not where the sea usually is, but it's where it gets to at its high points. So particularly, as I mentioned, during periods of flooding, storm surges, king tides, tsunamis, and other severe weather events like that. It's where the water ends up at the high point that's the problem, and sea level rise makes that situation worse. Plus, of course, we talked about how there's an increase in the rate of extreme weather events. Well, that makes that even more of an issue, particularly in coastal regions. And these effects of sea level rise, as well as increased temperature rises, can also have flow-on effects on coastal ecosystems. So it can lead to loss of mangroves, for example. Also, it's expected that crop production will decline because of salinization of irrigated water in coastal regions. Effectively, if sea levels rise, that leads to ocean water pushing inwards further inland, pushes further inland, thereby contaminating any water that's drawn from the soil in those regions. Damage to ports can also disrupt sea trade. So there's many effects here resulting from higher sea levels, and not just the average level of sea levels, but also where the ocean ends up as a result of flooding and tsunamis and such. Another important fact to remember is that the oceans are currently very far from equilibrium. Even if current temperatures stabilize, so there's no change in temperatures, the ice will continue to melt, and the thermal expansion of the oceans will continue, which will eventually lead to sea level rise of dozens of meters over the next tens of thousands of years. And that's if current temperatures stabilize, let alone stabilizing greenhouse gas levels at the high level that they're likely to reach by the end of the century. That will lead to even more temperature increase, and therefore even more latent sea level rise. So over the coming millennia, Earth is effectively committed to many dozens of meters of sea level rise. It's just that this takes a very long time to happen. So whether this is a problem right now is sort of questionable. I mean, we don't really know what's sort of going to be happening with respect to global population distribution in 2,000 years' time. That is a lot of time to adapt. But even so, it is something to bear in mind that it's not just the amount of sea level rise that happens in the next 80 years or so by the end of the century, but also what's expected to happen in centuries to come. And there's a potential very large loss of economically valuable, not to mention sort of culturally and historically valuable land areas around the world if we actually did allow sea levels to rise by many meters in the next 1,000 years or so. So that's a longer term issue, but still another effect of sea level rise resulting from climate change. Yet another issue with the oceans, as if we haven't already raised enough, is that increased ocean temperatures can lead to substantial changes in ocean currents. So this can include those involved in the North Atlantic Current, which helps to warm northeastern Europe, and the El Niño Southern Oscillation, which is a very important mechanism that has effects over the entire world. It's not really currently known very well what these impacts are likely to be, but it is known that changes in temperature, even fairly small changes in ocean temperature, can have significant effects on these currents, potentially disrupting them or changing how they work. And that will potentially have very large effects of rainfall patterns and average temperatures in parts of the world, especially Southeast Asia and Northeastern Europe. So as you can see from the list of different issues that we've talked about, from ocean acidification to coral bleaching, sea level rise, and changes in ocean currents, climate change has a very large effect on the Earth's oceans, arguably more so than even the atmosphere, as sort of counterintuitive as that might seem. And as important as the oceans are, obviously, to humans and to the planet as a whole, that's definitely something to be aware of. But let's now move from talking about the oceans to talking about ecosystems. I mean, we've already talked about ecosystems in the ocean, but particularly ecosystems on the land now. Now, once again, we've already talked about how climate has changed dramatically throughout Earth's history, but again, that typically takes thousands to tens of thousands to millions of years, and that gives ample time for most animal species to migrate, plants to spread through dispersal of seeds, long-lived organisms like trees to grow in new environments, and evolution to also have an effect at helping the organisms to adapt to changing conditions. Currently, the climate is changing far faster than previously, tens to thousands of times faster, depending on which periods of time you're looking at, but much, much faster than previously has been the case. And that means that many ecosystems don't have the same amount of time to adapt as they previously have. They'll adapt eventually, of course, but the question is how much disruption occurs in the meantime. Climate change is already known to be a major driver of biodiversity loss in many different types of land environments. This includes cool conifer forests, so particularly up in northern latitudes like Siberia and Canada, savannas, so particularly parts of sub-Saharan Africa, Mediterranean climate systems, tropical forests, and Arctic tundra. All of these land types are particularly vulnerable to climate change. Forests especially have a particular vulnerability because many types of trees, it turns out, are highly sensitive to changes in temperature and rainfall. And unlike animals, trees cannot move, and they also take a very long time to grow, unlike other types of plants, which can grow more quickly. So forests, it's especially hard for them to adapt, and they're particularly vulnerable to these changes in temperature and rainfall that are occurring as a result of climate change. And so a large fraction of boreal forests will be threatened by increases in global temperatures over coming decades. Other ecosystems that are especially at risk, well, coral reefs, I've already mentioned those. Mangrove swamps, I've already mentioned those too. Polar and alpine ecosystems because of the temperature sensitivity there. Wetlands and native grasslands. There's much more that can be said about the particular impact on these ecosystems, but I'll leave that for another time. The IPCC currently estimates that at 2 degrees of warming, so that's actually their lower kind of target of what we're hoping to achieve by the end of the century, and probably it will be more than that, around 10% of species on land would become critically endangered. I'm not sure what the figure would be for 3% of warming, but you can be sure it'd be higher than that. And 10% of species being critically endangered is pretty severe. That could have very substantial disruptions on ecosystems. It's not going to destroy completely, of course, all of the ecosystems in these places, but it will severely disrupt them. Exactly what value you place on ecosystem loss is quite controversial, but ecosystems play an important role, not just for their own sake, but also for scientific purposes, scientific research, discovery of drugs, many of which come from the natural world and various types of plants. Sources of course, meat for some of the world's population, especially fishery. But also the fact that we rely on the ecosystem for many core services, particularly the production of oxygen, much of which is produced by tropical forests as well as boreal forests. And so we need those forests as well as the vast array of animals and insects and other types of plants that sustain them in order to produce the very air that we breathe. We rely on ecosystems to produce soil that we grow plants in and many, many other benefits that we get from the ecosystems more or less as they currently are. So 10% of species becoming critically endangered would massively disrupt these ecosystems. Let's talk about now the effects on agriculture. So rising temperatures and changing weather patterns often result in lower crop yields compared to if we kept the temperatures the same and weather patterns the same, largely due to increased water scarcity because of drought, flooding, and more severe heat waves. So the major issue appears to be actually water availability and not the direct effect of temperatures, because crops do respond to changing temperatures. Some crops do well at high temperatures compared to others. In general, crops are already grown in climactic areas where they're well suited to, and so changing those climactic variables will typically make things worse, but that's not true everywhere, that's just overall. But it appears that the direct effect of that is smaller compared to the effect of increased water scarcity. Now that can potentially be overcome through things like desalination and better irrigation practices, but we need energy in order to be able to supply water in the needed areas. And then of course we have to question, well, how do we get that energy? How is it generated? Is it generated in a way that's going to further increase temperatures and so forth? So that's a significant issue. Another issue is that many varieties of crops, particularly those grown in sub-Saharan Africa, are already grown fairly close to their limit of their heat tolerance, meaning that higher temperatures will directly lower yields for those cases. That's not the case for all crops, but for some crops, and especially, unfortunately, those grown in sub-Saharan Africa, which is some of the most vulnerable regions of the world to famine, are those that are most likely to have negative impacts as a result of increased temperatures. Another problem is that many pests and diseases are expected to become more prevalent or spread to new regions as a result of increased temperatures. So that's mostly going to have an effect on the world's livestock, which are expected to face many of this increased disease burden, as well as greater heat stress on animals directly. Now, some people will talk about the fact that plants benefit from an increased concentration of CO2 in the atmosphere. That's called the CO2 fertilization effect. That does offset some of the detrimental effects on agriculture due to climate change. And we'll talk in a moment, and just a little bit, about how we can sort of balance those and make an estimate about what the overall effect on agriculture will be. But it's important to bear in mind that just because there are some benefits to agriculture because of the CO2 fertilization effect doesn't automatically mean that on net, agriculture will be easier or yields will increase as a result of climate change, because there are many offsetting factors as well. And of course, it does vary by region. Now, the IPCC estimates that without adaptation, so if we just sort of continue to do things the way we do them now, the effects on yield would be, as a result of increased temperatures and also the factoring in the CO2 fertilization effect, will be fairly small for rice, and that's predominantly grown in Asia. But it'll be fairly large for maize, soybeans, and wheat, about 10 to 20% of a reduction in yields due to higher temperatures. And as a result, effects are much worse for Africa and South America compared to Europe and North America, and partly that's because of greater availability of things like fertilizers and irrigation in developed regions compared to undeveloped regions of the world. So there's quite a lot of regional variability. And though it looks like Europe and North America will do fine, there may be a slight reduction in yields of certain crops, but there's already far more than enough food produced in these regions and they'll be able to readily adapt. That's not really the issue. The issue is not, will the world's developed countries be able to adapt to changing agricultural requirements as a result of climate change? The answer is almost certainly yes. But the issue is, will the world's most vulnerable regions be able to adapt, and over what time span will that occur? And that seems to be really where the problem lies, especially in sub-Saharan Africa, which is going to be most vulnerable to the reduction of yields in things like maize and wheat and some of the other grains that are widely grown there, where there's, as well as on top of there being an increased drought and decreased ability to supply water to these crops in areas where there's least ability to adapt. So that's really where the issue lies with respect to agriculture. It's the world's most vulnerable regions and the difficulty of adaptation there. Not so much that there's going to be an overall problem with feeding the world's population. You know, like currently, the issue is getting the food reliably and nutritionally adequate food to the people most in need of it, and that's going to become more difficult as a result of climate change in the coming decades. Now, I want to briefly mention the notion of tipping points. I could do a whole episode on this, but I just here want to mention it because it's something that should be said at least briefly in a podcast on this, on the effects of climate change. So the IPCC defines a tipping point as a critical threshold beyond which a system reorganizes, typically abruptly and possibly irreversibly. Now, that's very vague, but here they're talking about the climate system. And so a tipping point in the climate system is a threshold, and particularly we're thinking of a temperature threshold or a CO2 concentration threshold, after which or at which the climate system will abruptly change or possibly irreversibly change. And these thresholds can be brought on by a small disturbance that produces a disproportionately large change. A simple example of a tipping point is if you have like a glass of water on the edge of a bench, right? And initially it's fine, it sits on the bench, you push it a little further, it's still fine, the center of its mass is still lies on top of the bench, and so it stays on the bench, right? You push it a little bit, nothing happens. But once it gets to a certain point, you can give it the tiniest little nudge, and it will fall off and smash on the floor. The point is here that a tiny disturbance resulted in a critical threshold being surpassed that results in a very substantial change in the system. Now, instead of your glass of water sitting on the bench all nicely, it's all over the floor and the glass is smashed. So that's a simple example of a critical threshold or a tipping point. So those can exist in very simple systems like a glass of water on the bench, but they can exist in complex systems as well, and they can be harder to predict. So in 2022, or as of 2022, the IPCC identified 9 global tipping points that they think are likely to occur or may well occur as a result of climate change. And they expect that 4 of these 9 are likely to occur if warming surpasses 1.5 degrees, which realistically means that they're basically certain to happen because it's very unlikely that we're avoiding 1.5 degrees. So in particular, collapse of the Greenland ice sheet, these are the 4, collapse of the Greenland ice sheet, collapse of the West Antarctic ice sheet, coral reef die-off, and boreal permafrost thaw. And really, we're already seeing these sorts of things happen, but there's an expected threshold point at which the rate at which these occur will dramatically accelerate. Now, from what I understand, the important point about the Greenland ice sheet collapse is that once we reach, certainly, let's say 2 degrees Celsius, the Greenland ice sheet is pretty much guaranteed to disappear long term. The Greenland ice sheet essentially can't survive in a world with more than about 2 degrees warming relative to pre-industrial levels. However, the rate at which we lose that ice sheet it's important to factor that in because it's not going to disappear overnight. There's far too much ice. From what I've read, it's likely to take thousands or even tens of thousands of years for the Greenland ice sheet to completely melt. So even if we pass this threshold, likewise for the West Antarctic ice sheet, it's not going to collapse overnight. It will collapse fairly quickly in geological terms, but not in human terms. There has been a little bit of debate about that. I have seen a few people question, could it melt much faster? But it does seem pretty well agreed that these ice sheets will take a very long time to melt completely. So that doesn't mean we shouldn't be concerned, but it does, we should consider it in the context of what's likely to happen, which is that we will be losing these ice sheets and that will result in very substantial rises in sea levels, but that will take thousands of years to happen. Anyway, so loss of the West Antarctic ice sheet and the Greenland ice sheet are likely to occur, or at least to begin, as a result of these tipping points this century. The 2 other ones, coral reef die-off, we're already sort of seeing that happening, and that's going to become more pronounced. And permafrost thaw, particularly in northern Canada and in Siberia. That's likely to become more of a significant issue and lead to severe disruption in those ecosystems. A couple of the other major global tipping points that they identified are dieback of the Amazon rainforest, cessation of the North Atlantic current, collapse of convection in the Labrador Seas, I don't know too much about what that one is, collapse of Antarctic winter sea ice, that one won't result in sea level rise, because remember sea ice is different to continental ice, but that will also be significant effect. Loss of the East Antarctic ice sheet, and also loss of subglacial basins in the East Antarctic area. So you see there's lots of effects here at the poles. In fact, all but 2 of these are effects near the poles. The main one that's not being Amazon rainforest dieback and the cessation of the North Atlantic current. So these will all be quite significant effects on the globe if they occur and to the extent that they occur, and we'll sort of have to see over time. But the important thing is that it's not always predictable exactly when these things will happen, and a small change can lead to a small initial perturbation can lead to a very substantial change in the system. Okay, so let's move on and talk about the last couple of issues, which is mitigation and the costs of the impacts and the costs of mitigations. So I've talked about some of the impacts of climate change with extreme weather, various effects on the ocean, effects on ecosystems, effects on agriculture, and some other tipping points, particularly around the poles. But can we get a way to kind of aggregate all of these impacts together, as well as some of the benefits, like the fertilization effect of CO2, for example, and more land being available for agricultural use in certain areas, like in Canada, for example? There are some benefits, though I think certain people grossly exaggerate those relative to the costs. But what we want to do is get a sense of the overall effect in some sort of integrated way of climate change. How big of a deal is it going to be, let's say, at least in this century? How much of a disruption will it be? It's very difficult to do that because of the vast range of different types of effects that it will have, especially quantifying the impacts on ecosystems is very difficult. But there have been a number of estimates that have been made. And in particular, I'd like to discuss one study that I found in my research that I find particularly credible and I think provides a very good basis for estimates. So this paper, which was published in Nature Climate Change in 2023, is called New Damage Curves and Multimodal Analysis Suggest Lower Optimal Temperature. And it's by far the best of these sorts of estimating the cost of climate impacts and adaptation studies that I've been able to find. There's a review of the literature in the IPCC report, but it doesn't include this paper because it came out afterwards. And the range of estimates in the IPCC report is very high. But this more recent paper, I think, does a much better job. It uses better quality evidence and more consistent methods of integration, and their overall finding, so first I'll say what costs they included. So they included the costs of changes in crop yields, loss of production of forests, loss to fishing catch, loss of land due to sea level rise, increased damage as a result of increased rates of flooding, damage to roads from climate change, changes in the efficiency of wind and solar production. I'm actually not sure if that's positive or negative, but they factored that in. Increased demand for energy and reduced labor productivity due to heat. It's harder to do physical labor in higher temperatures, and you can estimate the effect of that. So those are the effects that they included in their analysis. Aggregating that together and factoring in changes in the world's economy, they estimate that 3 degrees of warming relative to pre-industrial levels would result in a 10% loss of global GDP by 2100, so by the end of the century, compared to only 2% lost GDP for 2-degree warming. So this 10% or 2% figure is not a one-off amount. This is every year. World GDP is 10% lower than it would otherwise be, and that's an enormous cost. That's trillions of dollars of damage every year as a result of climate change. They also considered the costs of abatement, so that's mitigating climate change, reducing emissions, and it really depends here, and this has plagued the literature for a long time. Ratio of costs and benefits depends on the discount rate that you use. Discount rate refers to how much you discount or reduce, effectively, benefits that occur in the future relative to costs that occur now. So we can incur costs now by paying more for energy, effectively, investing in green energies, which will reap benefits mostly in decades' time when they will prevent damage that would otherwise occur. But those benefits will mostly be realized in the future, whereas the costs need to be borne now. And so in economic analysis, you always want to add a discount rate to factor in you can think of it as opportunity cost, right? I could invest in solar panels now to reduce my energy usage and save money there, but then I could do other things with that money. I could invest it somewhere or earn a return somewhere else. So you want to factor in that lost potential benefit that you could have done other things with those resources, right? But it's very controversial what the discount rate should be. I tend to think that the discount rate should be relatively low, probably the rate of economic growth, about 2% per year, I think is a reasonable discount rate to use for this sort of analysis. And I think that is roughly what was used. I think that the consensus is leaning towards lower discount rates than some have used in the past. But at any rate, in their analysis, they estimate the benefits of abatement to exceed the costs by about 2 to 3 times in net present value. And so essentially what this means, according to this analysis and many others, although they disagree on the exact quantities, I find this one particularly plausible, is that mitigating greenhouse gas emissions, reducing emissions, is essentially a bargain. That doesn't mean we should reduce emissions an arbitrarily large amount arbitrarily quickly. We shouldn't stop all emissions tomorrow. That would not be a good idea. But we should be doing what we can to reduce emissions quite quickly. And the reason for that is because we can incur a relatively modest cost now to gain a very large benefit in the future by reducing these costs that would be borne, particularly in later decades in the century. It's also important to note that there are many costs of climate change that are not incorporated in this analysis, and they explicitly identify that. So things that are not included are the financial costs of ecosystem damage, because really no one knows how to quantify that. Losses as a result of increased health burdens from higher temperatures, like during heat waves or increased tropical diseases and things. That's likely to not be trivial. Increased extreme weather events. So as far as I know, they factored in flooding, but not other extreme weather events like hurricanes and droughts. Increases in food insecurity in certain parts of the world, and an increased rate of tropical diseases. So I think that the two really big ones there would be economic burdens from higher temperatures, the health costs of higher temperatures, and the ecosystem damage. Those are likely to be quite large. And those weren't incorporated into this analysis at all. So they could easily substantially increase even further the lost GDP due to climate change. And the choice we really have at this point is between 2 and 3 degrees of warming. 3 degrees seems likely what will happen if we just sort of do current business as normal, so like current pledges and trends. 2 degrees is maybe the best we could achieve if we, really push for net zero in the next decade. We might be able to achieve around 2 degrees of warming. So that's sort of the range that we have available, between 2 and 3 degrees of warming by the end of the century. And these analyses show that if you factor in these extra costs and assume that's probably a few more percent added on above this estimate here, that we're talking maybe a difference of 10 percentage points of global GDP by the end of the century, compared to if we go for the 2-degree warming compared to the 3-degree warming. And the costs required to achieve that reduction are nowhere near the amount of benefit that will be accrued. The costs of abatement are known fairly well because we sort of have a reasonable idea about how much it costs to impose carbon tax and other things like that. It's harder to estimate what the benefits will be because the impacts of climate change are more uncertain. So the point is that it's likely that investment in abatement and mitigation will substantially pay off of earning multiple times the amount invested in net present value terms. And of course, as I said, depending on the discount rate that you use. Now, bringing everything together, let's talk briefly about climate mitigation. What can be done to mitigate or to reduce the amount of greenhouse gases that we're emitting and to bring down the eventual global temperature rise? Well, fundamentally, what needs to happen is that electricity production needs to shift away from coal and natural gas towards solar, wind, and other renewables. That has already been happening to a very substantial extent over the past 20 to 30 years. In many parts of the world, it's already cheaper to add new capacity in solar and wind than it is to add it in coal or natural gas. It does depend exactly on where you are, but that's true for many parts of the world. However, a major challenge for electricity production is the need to store energy between when it is produced and when it's consumed. Solar and wind have the downsides that they're highly seasonal and diurnal, I guess, as well. Solar obviously is only produced during the day, and there's more daylight during summer than in winter, and tends to be less cloud cover as well, which is another factor. Wind is highly variable by day and by season and by place. So we need to find a way of storing that energy for when it needs to be used. The big challenge, of course, for solar is that typically you generate most of the energy during the day, but the highest energy demand is often in the evening when you don't have much, if any, solar generation. So you need some way to bridge that gap. Chemical batteries are currently far too expensive and inefficient to serve this role at large scale. And it's not just an issue of cost, but it's also an issue of the sheer quantity of rare minerals and other materials that would be needed to build batteries of that magnitude. So they are not really feasible. Current chemical batteries cannot do the job at large scales of storing that amount of energy. So we need to develop alternate storage mechanisms as well as improvements in the power distribution systems, which are also often not up to scratch. But that's sort of within known technologies. What's outside of known technologies is a sufficiently reliable and cost-effective energy storage system that can be used to store renewable energy for when it's needed. Now, there's many possible technological solutions to this. I'm not going to go into them here because that's sort of outside the scope of this podcast. But I don't think anyone seriously thinks that we won't find something that's appropriate, and probably there'll be many different solutions for different places. But it's an issue of time and resources, right? So we need to devote more resources to research and deployment and testing of these systems to work out what's going to work best, and that needs to be done sooner rather than later if we're to achieve the lower global warming targets. In addition to switching the energy production methods, there also needs to be improvements in energy efficiency, so particularly better construction methods and design of cities. There needs to be a decrease in reliance on private cars. They burn a significant quantity of fossil fuels, and greater use of mass transit, cycling, and walking. This is not just an individual choice issue. Partly it is, but it's substantially an issue of city planning and design, where things are located, laws about building size and about where money is invested in mass transit versus road building, and taxes or subsidies for fossil fuels and other things like that. So there are many different public policy areas that are affected by this, or that have implications for this. Another major factor is that we need a shift away from animal agriculture towards plant-based diets. Animal agriculture is a major cause of greenhouse gas emissions, both directly by flatulence, reducing methane for cows and things like that, in addition to clearing land for use by animals, which results in release of the carbon stored in the foliage that was there into the atmosphere, plus everything else like the transportation of meats and other things like that. It all adds to greenhouse gas emissions, and animal agriculture is a far less efficient source of calories in terms of the amount of energy that's needed to produce the same amount of calories, because it's at a higher level in the trophic food chain, right? A high trophic level. So essentially, you have to pay much more energy to get the same amount of calories in meat compared to in grains or other plants. In general, of course. I mean, there can be specialized cases where certain plant foods might be very energy intensive, like if they need a lot of water, for example. But speaking generally, animal agriculture is far less efficient. So there needs to be a shift away from that. There also needs to be a reduction in deforestation and a promotion of afforestation or reforestation in many areas of the world. That's already been happening to a significant degree in Europe. There are already more forests in Europe now than there were about 100 years ago. And that needs to happen in other parts of the world as well. And it's a big challenge because many parts of the world that are most vulnerable to deforestation, such as tropical regions, are also, in many cases, very poor and underdeveloped areas where it's hard to enforce laws against deforestation, and it's also difficult to really motivate people in the local populations to care about these issues when they're just trying to survive day to day. it's in their interest as well, but it's harder to get people on board when there are many other difficulties that they face, and they may not have other opportunities other than working in, illegal logging or slash and burn agriculture and things like this. So there are challenges there that need political and social solutions beyond just sort of technological ones. And just sort of to wrap this up, climate change should be viewed as a global problem because it is a global problem. No one country or one part of the world can resolve climate change by themselves, and it wouldn't really make sense to try to do that anyway. It needs to be considered in a global context, and because there are many facets that affect it. We've just talked about them in terms of electricity production, industry, energy efficiency, design of cities, animal agriculture, the many different factors that affect that. So global coordination is needed, and it is encouraging that there has been a lot more of that in the past 10, 20 years than there was prior to that. That being said, as I mentioned, the current trajectories and pledges are still insufficient to get us to that 2 degree or lower of warming, which is ideally what we'd like to achieve. Current trajectories and trends and pledges have us achieving more like 3 degrees of warming by the end of the century, which will result in very substantial economic costs. The estimates indicate that civilization will continue, will survive, but many of the most poorest and most vulnerable parts of the world will suffer dramatically as a result of climate change. And I think it's incumbent on all of us to try to do our part as individuals, as consumers, as citizens in our political systems and so forth, to promote the policies that will lead to appropriate and effective reductions in greenhouse gas emissions and other improvements to improve energy efficiency and so forth, so as to facilitate achieving, or at least getting as close as we can, to the lower band of these temperature rises, so as to reduce these costs. But a full discussion of all of these socio and political issues goes well beyond this podcast, which is a science podcast, and so I'll stop there at that point. Thanks everyone for listening. I hope that was interesting and not too depressing. I think, again, there are things to be optimistic about. There are positives, but there are also many negatives. And so understanding the issue is hopefully at least a first step towards doing something about it. So hopefully you've learned something here. If you would like to support my work in science communication, there's a number of ways to do so. You could give the show a favorable review on iTunes or Spotify or whatever aggregator you like to use. Those are always appreciated. You could also go to my YouTube channel, the Science of Everything podcast on YouTube, and like some of the videos there. I'm just starting to move the show onto YouTube, as I've been talking about for some time now, and the channel is still quite small, so any support that can be given is really appreciated there. Even a few likes can make a big difference at this early stage, so that's much appreciated. If you'd like to make a financial contribution, you can do so in 2 ways. You can send me a one-off donation via PayPal to my email address, fods12@gmail.com, or you can become a recurring donor via Patreon and pay per episode. So you can just type Science of Everything podcast Patreon and become a supporter there. I really value and appreciate all my generous financial backers for helping me to devote more time and resources to the show, including paying some editors to help me bring the podcast in a visual form to YouTube, which is what I've been devoting substantial resources to over the past year or so. So I really appreciate everyone who's contributed to that. Also, if you'd like to get in touch with me, you can email me. As I just said, my address is fods12@gmail.com. That's FODS12@gmail.com. So, that's all we have. Thanks for listening. I'll talk to you next time.